Hello, everyone, and welcome to the Chapter 10 lecture for Auto 105 Manual Powertrains. In Chapter 10, we're going to be looking at the different drivetrain sensors and testing that goes along with that. Unlike other vehicle systems, manual transmissions do not have that much electrical going on in them. But as we integrate smart differentials, transfer cases, and active driving systems, we will have more computers operating different systems as we start to move forward. So it is something that we do have to have a good base behind looking at electrical systems to get us able to diagnose these cars correctly. All modern vehicles within the last 25, close to 30 years now, are operating on closed area networks, otherwise known as CAN systems. Drivetrain components, much like the engine and occupant safety components, all fall under the CAN C or chassis communication leg of the vehicle system. Now, this is the fastest regulated closed area network. What I mean by regulated is closed area networks, and CAN C is regulated by OBD2. So this is a system that came out in 1996 that made standardization of all vehicle diagnostics ports for the use of emissions across the United States. So that's that diagnostic link that we're all very familiar with. This then allows for us to have similar CAN communication networks amongst all vehicles. That being said, though, within the last 5 years, a lot of manufacturers have come up with faster networks for different systems that operate at a much faster rate, typically in the telematics or the infotainment system. So it's not the fastest one anymore, but it is still very, very fast in how much computing power it has. As I stated before, manual transmissions will not have a computer. They tend to only really have two or three sensors, but there's going to be factors that will limit our transmission operation, and that'll be all done through the PCM. Now, the PCM is going to have a computer. It's going to have its own electronic control unit, otherwise known as an ECU. PCM or powertrain control unit can be another name for it. Doesn't really matter, i.e., it is the module that is going to function as the decision-making system for the vehicle. It's going to be looking at all of its inputs, and the inputs might be inputs given to it or communicated to it via the CAN-C system. And then it's going to have the ability to correct and adjust how the vehicle is operating, what it sees via the inputs to its outputs. We also have the ability for it to have an algorithm in it to where we can figure out what the best operating characteristics are going to be. So there's going to be set parameters that the vehicle will be in. And if we fall outside of those set parameters, the computer can correct or set a diagnostic trouble code. It also has the ability to store memory. There's short-term and long-term memory. Short-term memory is usually 120 seconds, and that's going to be 60 seconds before an event occurs and 60 seconds after an event occurs. And then there will be long-term memory that will be stored and sometimes indefinite. When we start to get to permanent diagnostic codes on modern vehicles, some of those systems can store information for the life of the computer with or without voltage. The ability for us to have storage of diagnostics information and freeze frame data allows the mechanic to more accurately diagnose a vehicle. Why this is important with manual transmissions is quite often you can look at the transmission acting funny or the vehicle driving irregular and blame the transmission when ultimately it can actually fall down to something else. For instance, with drive-by-wire vehicles, it may be that the operator, trying to give the car more throttle, but it won't. Now, the transmission has the ability to communicate as an input to the PCM what gear it's in. Usually there's a shift location sensor, and then that can, tell the transmission if we're in neutral, if we're in drive. And a lot of times that can throw customers off because it will act differently in each one of those gears. So it is something that we do have the ability to have memory checked so that we can look at, was there another sensor that potentially was causing issues with my transmission that has now resulted in the vehicle having an irregular driving. A prime example of this is if there's a malfunction with the variable valve timing. Typically, the variable valve timing will either advance or delay the spark at a certain occurrence. From there, that can affect engine performance, which can also affect how the transmission is going to operate. So you may lose power, or it may kind of delay or give when the operator shifts gears, like a delayed amount of output torque, and therefore they might think that there's an issue with the clutch or there's an issue with a particular gear inside the transmission. However, if we look at diagnostic trouble codes that do set with any of these systems have an issue, then we can look at what will actually correct the concern. Now, the closed area networks or CAN systems will interlink almost all of the modules on the vehicle. Now, there'll be different CAN loops. Typical CAN loop for CAN C is going to have all of the chassis required modules that have to operate in a quick manner, not only for our operation of the vehicle, but also in case there's an emergency, in case there's a crash. This network operates really fast at 1 megabit per second of data, and that is over a twisted wire pair going to each module. Usually our modules are going to have the engine control unit, a transmission control module. If it's an automatic, if it's a manual, usually that data is sent straight to the powertrain control module or ECM for the engine. Our anti-lock brakes module or electric brake module, the final drive control unit or drivetrain control unit for the transfer case if it's four-wheel drive, and then occupant control module and airbag unit. We can also start to see vehicles that are electronically steered to also have that on top of our CAN C modules. The benefit to that system is if we look at this architecture that I have here, we have the ability to share data amongst different modules. So there's the ability for data to be sent and therefore multiple inputs given. Now the advantage to that is every module has a 2-wire twisted pair going to it, and therefore the data can be sent equally to all modules. Now there are a couple different styles of architecture that engineers can use. One of the things that we do want to have an understanding of is, you don't want to condemn one thing right off the bat. Now we can have what we have with like this area right here, and this is known as a hub and spoke, meaning that we have a central hub and then outside of it goes each spoke to each individual module, so that if one module goes dead, it doesn't affect the rest. We can also have a daisy chain, and that is what this leg of modules in. So the downside is let's say the SAS goes dead communicating. Well, that means we will also lose the W control module, WCM, which is usually for ignition and smart keys, and then the occupant control module, because those are all on the other end of the leg, and therefore that chain has been broken. Manufacturers will do that on purpose, though, to where if there is an issue in one of those safety systems, that the car then goes into a limp-in, and you get the full Christmas tree on the dash, and effectively that prevents the car, hopefully, from being driven with the safety system being down. But all of those systems will go through our data link connector. Our data link connector is a 16-pin connector. Again, a test question you're going to see. And we will be communicating not only over the CAN C, but also you can see on this, we also have the IHS or the CAN B bus as well. Oftentimes, vehicles now have multiple networks. You can have 8 to 10 networks now to which we can communicate all sorts of different data to all sorts of different modules when that is the case. Now, our CAN C is going to be consistent. Again, this is regulated by the feds, so there will be some consistencies with it. As I stated before, it is a twisted two-wire pair. Why is it twisted? Well, when we twist a pair of wires together, that helps shield against other frequencies that can affect the voltage going down that communication line. Typically, we're going to have them as twisted wire pairs, and they're going to be located internal to the wiring harness so that there's no interference coming from anything else. We will have a high side and a low side. Now, the high side is going to operate at voltages anywhere between 2.7 to 3.5 volts. The low side is anywhere between 2.3 and 1.5 volts. If you add the voltage together with both lines, that gives you 5 volts. So therefore, if I am doing diagnostics and I am measuring the output voltage on the high side at the PCM and it is at 5 volts, I know that the high and low lines have shorted together, and therefore I have to look for something that has gone awry, something that's smashed, or anywhere else that there can be damage. It could be damage in the computer itself. And the inverse can be that way for the low line system as well. Now, this can be double checked by checking resistance. Almost all systems have a 60 ohm terminal resistance for one of the two lines, meaning that if you measure 120 ohms, again, it's shorted together, and that communication line has an issue. Now, the modules do have the ability to set diagnostic codes for an issue with the communication line network. Those codes are designated with a U at the beginning of it. So we're very familiar with P codes or powertrain codes, and those are going to be codes that will be like P070 or 731, which is gear ratio error in first gear, and that's a generic powertrain code. But if we have a communication line issue, we will set a U code. So U0100 is a general module failure, meaning that there is a module that is not communicating correctly on the CAN-C network, and for us to look at it. Now, that is a generic code, and then we can have potentially other communication line codes pinpointing what module has gone down, causing us to have an issue with communication. Now, communication codes, U codes, are a little bit more difficult to diagnose. However, I gave you the breakdown of the voltages and I gave you the breakdown of the resistance. It's really not too terrible to diagnose. The key thing that we want to make sure of is we want to make sure that we are not damaging these pins or these connectors when we are probing them. So no T-pins, and using the proper back pinning tools and or inline tools. I personally, when I'm diagnosing these systems, I like to make my own tools out of old wiring harnesses where I will take apart connectors and find the male and female versions of the correct pins, and then make jumper leads coming off of those with an alligator clamp. That way there's no risk of you damaging the component, and you can simulate it actually being connected in the same way that the pins would have a friction fit if it was operational. And you may be thinking, that's great and all, but manual transmissions don't have any computer. What does it matter to me? Well, the PCM can manage how much output torque is going to be fed to that transmission. Therefore, it will affect the transmission as a whole. So the PCM has the ability, when certain parameters arise, it can pull back on timing. Therefore, it can restrict how much output torque the transmission can have. And because the transmission is multiplying and in sometimes speed multiplying the torque, that can affect how the vehicle is going to handle. Now, let's shift gears literally and move into some of the sensors that we will have on a manual transmission. A clutch safety sensor or a neutral safety switch is a sensor that a lot of vehicles now have to prevent a vehicle from being started without the clutch pedal fully pressed down. Now, the reason for that is if the clutch pedal is released, that means the clutch is engaged against the flywheel, and therefore any torque that is applied to the engine or out of the engine will go to the transmission, and therefore the vehicle can move on its own. So the risk of the vehicle driving away on its own is very, very high. Now that would mean that the motor has to have a lot of torque, and typically, unless it's real low friction, it will get bogged down and not rotate forward. However, it is one of those things that it is a safety system. Now, this system does get bypassed quite a bit by people. However, I have found it's a really good anti-theft device, especially for an older vehicle. An older vehicle that didn't come with a clutch pedal or a clutch pedal safety sensor. This is a great system to install on a vehicle, and it's really simple. It just interrupts the starter solenoid or the field signal solenoid, and it closes the contacts or opens the contacts depending on how you want the clutch pedal manipulated, and therefore it can be very difficult to kind of find and act as a kill switch if that's the case. So the way that it would work, as you can look at the diagram, is that going in between the ground and the field coil for the relay for the starter, that switch either connects or disconnects. Now, what's great with that is an average thief is going to look for power side connections. So, back when people would hotwire cars, they would be looking for a power side being interrupted. Very rarely are they looking at the ground. So this is kind of, buys time. And quite often, if a thief doesn't think they can get away with the vehicle very quickly, they will abandon trying to steal it. Now, you're going to have to deal with the damage and vandalism of the interior and everything, but I'd still rather have my car if that's the case. Now, other sensors our transmission can have is we can have a kick down solenoid. Now, a kick out solenoid or a first to fourth solenoid can be for some vehicles. And what it does is it locks out being able to shift into second gear and instead shifting from first straight to fourth gear. A lot of rear wheel drive transmissions will have this in place to try to improve fuel economy. And what it will look at is the PCM will look at what throttle response the driver is giving. That solenoid will activate, and then you will not be able to shift from straight down from first into second. The get around with that is just give it more throttle in first gear, and it won't ever get into that parameter. The other one that all transmissions tend to have is the backup light switch. This is a very simple circuit. It is open circuit until the vehicle is shifted into reverse, to which the two contacts are closed, and then 12 volts goes through the switch out to the backup lights. This allows the vehicle to indicate that it is being put into reverse when the operator has selected reverse to notify anyone, as well as to light up the back of the vehicle. That is the purpose on why they are white. Backup lights are white so that during a dark condition, you have the ability to see what's behind you to a certain degree. Most backup lights now are pretty small and they're inadequate. But it used to be when it was required, they were a lot larger, and the idea was that they would kind of guide you or light you in going backwards. We also may have speed sensors. So some of you have noticed on the transmissions that you're overhauling in class that there is a strange sensor on the differential on our transaxle. We can also have this on rear-wheel drive transmissions as well. Now, this is a speed sensor. Now, the speed sensor is the signal that the PCM will use to give to the cluster to tell it how the speedometer should go, as well as operating the odometer. This system will operate off of a voltage generating type signal, very similar to what you're going to see on wheel speed sensors. But instead, it's going to be calculated to give what the vehicle speed is and the distance traveled for the odometer. It is important to note that if you change the overall rolling diameter, either above or below what it was from the factory, that you do have to calculate and adjust for this speed sensor. Used to be when it was a mechanically driven speedometer drive, so I had to do this on my 64 Ford. You would change out the gear teeth and you'd change out the output gear going into the speedometer drive and you'd have to do the math based off of your tire's diameter. That way, you could accurately get the right speedometer within the realm of operation. More modern vehicles, however, though, are going to be either using a Hall effect switch or a voltage generating switch, and they are contactless and maintenanceless type electrical sensors that will read a how fast the tone wheel on the output shaft of the transmission is turning. So what they'll have going on is a magnetic field will be built up in the coil inside of the sensor, and every time the tone wheel has the tooth that is closest to the end of the sensor that breaks the magnetic field, and that then sends the PCM a signal that we've rotated at a certain amount. We'll also look at throttle position. Now, throttle position is going to be very crucial when it's a drive-by-wire system. But even when it's not drive-by-wire and it's just traditional port fuel injection with a throttle cable, we'll still be looking at throttle position to more accurately represent how much output torque the vehicle and the operator specifically is requesting. So in this case, we may limit how much we can engage the transfer case if that's the case. So if, for instance, you have a vehicle that you're trying to shift electronically with buttons or a knob into four high or four low, if it sees that there's too much throttle input, usually above 5%, it's going to negate you being able to shift into four-wheel drive. Therefore, that will affect how our drivetrain is going to react with that. Now, these systems are going to be potentiometers, meaning that as a blade moves across the sensor, it will increase the voltage, or sorry, not the voltage, increase the resistance that the sensor sees. Therefore, the voltage is dropped as it goes to the PCM. So usually we're going to have a reference that's around 4.5-ish volts at wide open throttle, but will vary from vehicle to vehicle. In some cases, we are not going over 3 volts. Why this is important is occasionally these potentiometers can have burned out sections. So if we look at a scope pattern between a functioning throttle position sensor and a non-functioning throttle position sensor, we can see right at about 3.5 volts, we drop down for a split second. That can give the PCM the confusion that the throttle has closed, and that will then cut spark and cut fuel ignition to where therefore the vehicle will have kind of a buck. And again, that can make it sound like or feel like there's an issue when shifting gears if it's happening at that time. Now, throttle position sensors do need to be verified, and it is very important when we're looking at electronic actuated throttle bodies that we make sure that they're cleaned correctly. Now we can see on this Equinox throttle body, I can see a whole bunch of carbon built up on the blade, and that can then cause the throttle to stick. We want to make sure that we are not spraying cleaner directly into the motor or directly on the throttle blade pivot points themselves, because we can run the risk of wrecking the throttle body and therefore damaging it. It's not a bad idea we can graph these with a scan tool as well. That will give us at least a general idea of if the sensors are working. With this system that is drive-by-wire, meaning that there is no throttle cable going to the throttle body itself, it will have 2 throttle body position sensors, and on the accelerator pedal, we will have 2 accelerator pedal positions, or APP. Now, the important thing to remember with that is that the 2 sensors are going to bias themselves. So we'll have maybe throttle position sensor 1 is going to be at 4.5 volts at closed throttle and 1.2 voltage at full throttle, to where TPS2 can be at 1.2 volts at idle, and then 4.5 volts at wide open throttle. And then the APP will correlate the same way. Why we do that is that allows for redundancy so that we can see if there's an issue, therefore the vehicle can't accelerate on its own. I want to make very clear, these systems have been around for close to 30 years now. They are very reliable, It is very rare that I ever have an issue. In fact, for the first time in a very long time, I had where I replaced the accelerator pedal and it fixed the car. Normally, they very rarely throw codes and they very rarely go bad. So do keep that in mind when you look at diagnosing these systems. Quite often, we're looking at we have a wiring issue or a module issue that we need to correct ahead of time. Another way that the PCM is going to look at engine load to possibly detorque the engine if there's an issue with traction is through the manifold absolute pressure sensor or MAP sensor. Now, the MAP sensor is looking at intake vacuum. When the throttle blade is almost completely closed at idle, engine vacuum will be at its highest. We'll have the most vacuum or lack of pressure inside of the manifold. As we start to accelerate and the throttle valve opens and the intake valves are ingesting more air, the intake vacuum begins to drop. That, along with our throttle position, can be calculated what the exact load is for that engine. Therefore, if there is a situation where one of the wheels begins to slip, like we were talking about in our electronic limited slip differential lecture, the PCM has the ability to regulate that back and to cut throttle as one of the options it has. Now, if we don't have a MAP sensor, it is a MAF sensor or manifold airflow sensor. Those tend to not be used for calculating load to deregulate power at that point. Manufacturers will also look at crank position. Now, crank position is important because the crank position is going to tell us where on the firing order we have each particular piston. It will also allow us to look at how much output torque we have once compared to our wheel speed and or the transmission speed sensor, because we'll have a reference on what the different rotations of each one is. It's important to remember that in underdrive gear scenarios where we have a smaller input to a larger output, that the PCM will calculate that we are in first gear by looking at the difference in RPM between the engine via the crankshaft position sensor and the output sensor of the transmission. Therefore, it can calculate how much output torque is going down to the ground, and thus we can communicate that over CAN-C to go to the electronics limited slip differential or locker to determine if we do need to limit how much torque is going to the back wheels. Now, the crankshaft position sensor is going to be a pulse width modulated signal. And what makes it different than the other sensors we've talked about that are pulse width modulated and or voltage generating is we will have a larger cutout for cylinder number 1 at top dead center, or TDC, and that will be used for properly timing the engine for fuel and spark. Other electronic sensors that we can have on a modern drivetrain system are going to be through our transfer case. As I brought up before, looking at the throttle, we might not be able to shift into 4 high or 4 low if it is a electronically shifted transfer case. Most manufacturers have gone this route. In fact, with the exception of the Jeep Wrangler, I don't know of any other four-wheel drives you can buy in the United States that are not electronically shifted. Now, what this allows for is a vehicle to look at the different operating characteristics to either shift it into four-wheel drive if the proper parameters are met, or to deny shifting into four-wheel drive if they are not met. More often than not, it will give you a message in the cluster if there is an issue with trying to shift into four-wheel drive. Now, this will put on a light in the cluster and it will be flashing during the potential shift into four-wheel drive. If it doesn't go solid, indicating that you're in four-wheel drive within about 10 seconds, there's probably an issue. Either you're not meeting the parameters or you have an issue where you're unable to have it because of a failure. Quite often, too, a lot of transfer cases will have a neutral position. So in the slide before last, we saw there was 4 auto, 4 high, and 4 low, but there will usually be a separate switch or a manual override to get the transfer case into neutral. Now, we get a transfer case into neutral so that the vehicle can be towed if that is the case. Often too, we can have different diff locks. Now, this photo is terrible, but it does indicate a diff lock. Now, why it's terrible is because the car that this was taken in is filthy. It's all dust around it. That's gross, but whatever. Occasionally, we can have a locking differential inside of our transfer case. Now, we brought that up when we were talking about transfer cases in a later chapter. But what this allows for is equal torque to go to the front and to the rear. So we'll see these on four-wheel drive vehicles and not all-wheel drive vehicles. Again, once the operator hits that switch, as long as the vehicle is operating in the correct operational parameters, it will lock that center diff. Now, these transfer cases will have the shift motor as a unit and sometimes with an integrated module. Now, there will be other added features to that. We will have the shift motor itself that will move the shift linkage to allow for it to shift from 2 high to 4 low. But we will also want to know and verify the position, and therefore we will have usually a Hall effect switch or an encoder sensor that will allow for the transfer case to broadcast what position it is in, not only to the cluster, but into the drivetrain control module or to the PCM. Now, if there's a failure in that encoder reading, then it will set a diagnostic trouble codes. These codes will be C codes or chassis codes. They are not specific to every vehicle, and they will be specialized for each make and model. It's important to make sure that we refer to service information anytime we deal with this type of code. And then to round out the sensors that we will have on our powertrain is we will have wheel speed sensors or WSSs. Now, these wheel speed sensors will communicate usually directly to the ABS module, and then the ABS module uses the CAN-C to send out if there is what the data is and if there's a fault. Now, we can have 3 different style of sensors. We can have a variable reluctance sensor, we can have a magneto sensor, and we can also have a direct tone wheel reading sensor. These sensors usually do need to be read off of with a scan, not a scan tool, but a scope. Excuse me. Sometimes you can read scan tool data, but you usually have to have the vehicle going really slow. You cannot tell a difference between the two if there's like a performance issue on the code when that's the case. But these can be used to detect vehicle slip. We talked about that in electronic limited slip differentials in chapter 11, and I go in greater detail on that. But if there's any type of variation between these, then we can have a fault that will set a diagnostic code. Now, to wrap everything up, I kind of want to go over the 3 main types of diagnostic codes. The first is going to be open circuit. So an example of an open circuit means that there is a lack of continuity between wires. So this can be due to a broken wire. The example of that is I'm going to be using intake air temperature sensors for that. So you'd have a P0112 intake air temperature sensor circuit low. Circuit low is an indication of an open circuit. Now this can be an unplugged connector or a pin pushed out or a rat going through and actually eating the wire and opening it. So this is an example that I had at work where I have 2 open circuits. You can see the 2 wires broken right at the electrical connector. For some reason, I don't know why, rats like to chew at the connectors right at the base of the pins, which make them very difficult to repair. Usually you can't just like strip the wiring back and solder them together because it will make it short, or you won't have enough of end of the wire terminal to fix it. And a lot of times you'll have to get a pigtail repair kit. This is a smaller amount of wire that will allow for you to properly pin it into the connector itself. And again, we're looking at rat damage, but we also you can have open circuit very often when we're taking a transmission or a clutch in and out. A lot of times, we saw this when we did the clutch in class a couple months back, that there's wiring going over the top of the bell housing. And if that drops down in the way of the bell housing to the mating surface of the back of the motor, that can be smashed and we can get an open circuit type scenario. The next is going to be shorted to voltage. Now, what this indicates is that voltage is on the power side of our circuit and we're not seeing it consumed. Meaning that if we have a code P0113 that's intake air temperature sensor circuit high, we have to where two wires are touching that they shouldn't. Ground and power are touching, or power to ground, or even to a signal. Now, this can be due to wires getting smashed. Again, Stuart Little chewing and the wire then coming together afterwards, excessive heat, or quite often water damage and water intrusion. Now, why this isn't important on powertrains is we can have the wires touching. You can also have where battery acid has leaked down and has caused the insulation to be eaten away, and that to cause the copper windings to touch each other. And that's what I have photoed here. This often happens on the wiring harness right below the battery. Quite often manufacturers will put flooded lead acid batteries in the engine bay, and so that they're easily accessible. They'll be kind of high, and usually below the battery tray they can have control modules. Well, what can happen is if the battery outgasses or it can leak electrolyte out, that will eat away the insulation, and then all the copper can then touch each other, and you can get a short to voltage very similar to what I have photoed here. And then the last one is going to be short to ground, and that is where the power wire has found ground quicker than it did when it got to the sensor. And the shorts to ground code is going to give you a reason to look for effectively smashed wiring. It's important to remember that when we look at electron flow, it's very lazy. It's going to go to ground as soon as possible. If it can bypass or not go through the sensor or the component, then it will do so. The last set of codes that you can get that are kind of troublesome to diagnose are going to be performance or rationality codes. Now, those codes are looking at that there's a set programmed algorithm the vehicle should be operating it, and the vehicle is operating just outside of that, but is functioning. So the PCM is going, hey, I don't like what's going on here. We're going to keep the vehicle running, but I'm going to set that performance or rationality code. That is where you do very much want to look at freeze frame data when you get those type of diagnostic codes. Now that covers kind of vehicle electronics in terms for the powertrain. I know it was kind of brief and I did add more info to it. It is important to remember that you do need to get good at diagnosing electrical systems no matter your skill level. Most vehicles are going to have electric systems on them. We're not in the day and age of carburetors and distributors anymore. Those days are long, long gone. So do get a basic understanding of electrical. It's not as complicated and as scary as you think it is. But I hope you found this chapter helpful, and I look forward to seeing you in the next one.